Well, hi, hello, namaskar. Myself Mahesh Prasad from Department of Physics. As you know, well, dear students, we are in a chapter that is nothing but kinetic theory of gases as well as its molecules. Well, so far we have discussed many concepts under this particular chapter. That is nothing but we have discussed different postulate of kinetic theory of gases, and we have discussed about velocity. That is in terms of root mean square velocity of molecules, and we have discussed the basic idea between the temperature of the molecule, the temperature with respect to its kinetic energy. Now, in today's class, we will discuss about the degrees of freedom. So, before we discuss about this, I'll take one example. That is nothing but what we will do if we get a superpower. What we can expect. Hope we can do n number of things we can do at a time. Correct? Now, similarly, don't you think your matter is nothing but if I speak about in terms of gas over here, don't you think your gas which consists of n number of molecules? Correct? So now, what I do here is that I'll take one chamber and which is filled up with some gas molecules, and I'll start heating the particular vessel over there. So what happens? Don't you think molecules of the gas which starts moving faster than before? Yes or no? Yes. So similarly, whenever your gas molecules are moving from one point to another point, it can experience, which is trying to get the energy. So similarly, your degrees of freedom, which is kind of the same thing, it is a total number of independent ways in which particle of the medium can gain energy. So there are different ways we can expect to get the energy from different with respect to various methods. So now, to get that particular way of getting energy from different sources, we have a general formula that is nothing but like n which is equal to, that is the 3p minus r. Now you may ask, what is the n, what is p, what is r? Now I'll make it clear, where n which indicates degrees of freedom, where n which indicates degrees of freedom of the particle, where p which indicates number of particle, where p which indicates what? Number of particle, where r which indicates what? R which indicates number of independent relation, number of independent relation with the other particle, with other particle, with other particle we can expect. So this is what exactly we can expect. This is the basic formula we are supposed to consider over here. That is nothing but n which is equal to 3pr. Now you can ask, how I can write n is equal to 3p minus r? Well, we'll try to prove that. So by taking the individual gas molecules, like the first gas molecule, we can expect diatomic, monoatomic gas. Monoatomic gas. First one we'll discuss. What could be the degrees of freedom for monoatomic gas? Monoatomic gas. Now, when you see the word mono, what comes to your mind? Mono which indicates what? Mono which indicates single. So similarly, since we have a single particle over here, which means mono, do you think this particular molecule or particle can have any relationship with respect to any other particle? No. So similarly, I can write by using this formula, n which is equal to 3p minus r. So r value can be taken as what? 0 over here, correct? And p value can be taken as what is the number of particles. So what is the number of particles we have? Is 1. So n which is equal to 3 into 1 into minus 0. So it is equal to 3 over here. So this could be the value for degrees of freedom for monatomic gas. Understood? Well. And similarly, we have second one, that is nothing but we are supposed to concentrate on diatomic gas. So let us write diatomic gas. Di in the sense what? What comes to your mind when I say di? So obviously two atomic particle comes into picture over here. So similarly, if I say 3p minus r, so since it is a diatomic gas, two particle comes into picture. So let us write two particle. Now what is the relation we can expect from one each other? That is nothing but one relation we can expect, and how many particles we can expect? Two particles we can expect. So similarly, n which is equal to 3p. P can be replaced by how much? This P can be replaced by how much? It is nothing but a 2. So 2 of relation is 1. So altogether we can expect 3 into 2 is 6. 6 minus 1 is 5 over here. So number of diatomic gases, number of independence way in which your particle can gain energy, nothing but in a 5 different way. In the sense, it can have a degrees of freedom of 5 over here. Understood? Well. And similarly, we have a triatomic gas. First one we'll discuss about linear triatomic gas. First one we'll see about linear triatomic gas. That is a triatomic gas. What do you mean by linear? Linear in the sense what? The arrangement should be in the linear order. So let us take three different molecules. One is here and here and here. So these two are connected in terms of a linear connection. But the thing is, how many particles we can expect here? We have three different particles. So let us say here is one particle, second particle, and third particle. Correct? So now, if you take the same formula, that is nothing but n which is equal to, that is a 3p minus r, where n is the number of particle, where r is the number of relation with respect to other particle. So what is the particle relation we can expect here? From here there is 1 and one more is here. So altogether we have number of particle relation is nothing but 2 relation we can have. So that's why number of independent ways in which your particle can gain energy can be, that is nothing but 3 of particle is 3 minus 2. So here 3 is the 9 minus 2, that is nothing but 7. So here we can expect 7 as number of independent ways, means the degrees of freedom for linear atomic gas is 7 we can expect. Okay? Well, and similarly we can expect for our fourth one, that is nothing but non-linear triatomic gas, which is nothing but non-linear triatomic gas. If you speak, what we can expect, since it is a non-linear, it should not be in a linear, which means I can place one particle here, and I can place one particle somewhere here, and I can place one more particle somewhere here. So now, what could be the arrangement I can expect? One relation from here to here, and next here to here, and here to here. Now, how many relations we have? It's 3 relations. So similarly, if I say n is equal to 3p minus r, so what is the p value I can expect? P in the sense number of particles. How many particles we have? 1, 2, 3 we can have. Yes or no? Yes. So I can say 3 minus 3 I can say over. So 3 into 3 is 9. So 9 minus 3, that is nothing but a 6. So though we have a 3 particle, here also we got a 7 degrees of freedom. But think about the non-linear triatomic gas, we can get 6 as a degrees of freedom. So to get this, we have to remember the relation that is nothing but n which is equal to 3p minus r is supposed to remember. Understood? So what is my degrees of freedom? It is a number of independent ways in which a particle can gain energy or get energy. So this gives your degrees of freedom. By having this idea, we will try to get one more basic law, that is the equipartition energy. Okay? Well. Well, so there is one law which you can see on the board, that is nothing but law of equipartition energy. So before we get into this, what comes to your mind when I say equipartition? What do you mean by equal, by the way? So equally it is distributed. How it is distributed? Equally among its degrees of freedom. Well, so according to law of equipartition energy is distributed equally in the sense, there is a particular law, that is nothing but for a dynamical system. What do you mean by dynamical system? The system in which is in a motion. So for a dynamical system in a thermal equilibrium, the energy of the system, the energy of a particular system is equally distributed. The total energy is equally distributed among its various degrees of freedom, and the energy associated with each degrees of freedom per molecule is equal to half kBT, where kB is the Boltzmann constant and T is the absolute temperature. What do you mean by absolute? What do you mean by Boltzmann constant? Is 1.38 to 4 minus 23 joule per Kelvin. So that was the value we expect for your kB value over here. Well, so what they are saying here? For a dynamical system in the thermal equilibrium, the energy of the system is equally distributed among its various degrees of freedom, because each particular molecule, each particular gas, based on the gas molecules, your degrees of freedom also varies, because we can expect for monatomic gas degrees of freedom is 3. In the 3 different ways it can gain energy along x-axis, y-axis, z-axis. Similarly, if I speak about diatomic gas, it can have degrees of freedom of 5 over there. And if I speak about linear triatomic gas, it is having degrees of freedom of 7. And non-linear diatomic gas, which is non-linear triatomic gas, which is having degrees of freedom of how much? It is around 6. So similarly, each degrees of freedom, which means energy is distributed among its various degrees of freedom, which is equal to, and energy associated with each degrees of freedom, which is equal to half kBT. So half kBT, which means each molecules can expect the energy of half kBT. For example, whenever molecules are moving, it should have some kinetic energy, yes or no? So if I speak about the kinetic energy that molecule can expect along the x-axis, so this is the x-axis, this is the y-axis, and this is the z-axis. X-axis, y-axis, and z-axis. So whenever molecules moves along the x-axis, it can gain energy of, I can expect half mvx square. Yes or no? Yes. So similarly, whenever it moves along the y-axis, it can expect it is equal to, that is a half mvy square, which is equal to what I can expect? I can expect that is half vz square, which is equal to each direction, each individual degrees of freedom, which is equal to half kBT, which is equal to half kBT. Now, if I add this, what is the degrees of freedom I can expect? If I do, I can expect half vx square, which is plus half vy square plus half mvz square, it is equal to, I can expect each energy level, that is a half kBt plus half kBt plus half kBt, altogether I can expect 3 kBt, because energy is distributed among its various degrees of freedom equally. So if I replace half kBt, if energy of half mv square is half kBt and half mv square is equal to half kBt, half dz square is equal to half kBt, if it is so, I can write 3 by 2 kBt. Correct? So this is what exactly we can expect. And one more thing we can expect, degrees energy per degrees of freedom of monatomic gas. The energy per degrees of freedom of monoatomic gas, we can expect that is nothing but 3 by 2 kBt. Similarly, for diatomic gas, we can expect that is 5 by 2 kBt. And similarly, we can expect for non-linear, for linear triatomic gas, we can expect that is 7 by 2 kBt, that is the energy per degrees of freedom. And similarly for non-linear atomic gas, we can expect that is 6 by 2 kBt, or we can write 3 kBt, which is nothing but the same. So this is what exactly we can expect under a law of equipartition energy. Okay, well, so what do you mean by law of equipartition energy? For a dynamical system in a thermal equilibrium, energy of a system, the total energy of a system, which is equally distributed among its various degrees of freedom, and each energy half mv square, each energy of a degrees of freedom, which is equal to half kBt. So this is the meaning of your law of equipartition energy. Well, okay.